Hello and welcome at IDEA StatiCa Connection presentation. And today with my colleague, we will be asking the most common mistakes that IDEA StatiCa users do in connection design and how can they avoid them. Today, I'm here with my colleague, Adam. Hi, Adam. How are you?
Hi, Anne. Pretty well. Looking forward to today's session. So let's roll on.
Let's roll. Nice to be with you today. I'm Jan. I'm with IDEA StatiCa as a channel manager, and I think that we can jump right into the topics. Let's take a look at the most common questions that IDEA StatiCa users have. The first one, what is the correct position of forces? The other, which model type is the right one? Third one, why do I get bold errors in the 3D if the 3D scene looks well? And last one, why can't I cut or use the splice operation on my stub? Okay, so Adam, let's take a look at the first one. What is the correct position of forces?
Okay. Well, I'll explain this gladly to all of you. Let me focus on my working screen. I will turn off this presentation. Accidentally, I have a nice example prepared on my desktop for today's session. So let me start with this first topic or question about the model type. Position of forces is the first one. So where can I find this in IDEA StatiCa Connection? It's here when I click on a member. There is forces in, and I have three options: in node, in bolts, and positions. So what does it mean, and how does it work, and when should I use what? So let's have a very simple example, just a column and a beam connected by a fin plate. Let's take a look at the fin plate operation. Everything is just normal, nothing special. I have inputted -45 of a shear force, and I want to calculate this model. Since I'll calculate it, I see my bolts didn't pass the code checks, even though I would assume they would. So I'm interested with what's going on. So I will take a look at stress. This looks okay. I'll take a look at strain and maybe take a look on the deformed shape of the joint. And whoops, take a look at this. This is not really looking reasonable, right? I have a shear force pointing down and the beam goes up. So this is something wrong. So if I go back to design and take a look at the wireframe model, I can see my position of the shear forces in the node. That is this black ball. And from the node and the shear force, there is a bending moment propagating as linear towards the free end. So actually, I have a moment in the bolt where the hinge is located, which doesn't make sense. And for this reason, if I go back to the options and I switch to bolt, go back to wireframe and take a look at the load effects, I can see now that the forces position is now shifted to the position where the bolts are. And here I have the zero moment and the hinge. So now let's take a look. How does it affect my analysis and result? And see, this is looking much better now. I have passed the code checks because my model now works correctly. And if I take a look at the deformations, this is looking very reasonable. Even if I scale up the whole deformation by 80 times, I can see that this is working very well. So this is why the position of forces is really important, and it's important to understand that. And so this was very simple, just to get in this topic. I have another example. Again, nothing special. This is a standard stub. If I go back to design, I can see I have two beams. I have a stub operation set all right, and I have a cut operation that welds this stub to the column. And again, I have a shear force in here. So when I calculate this as a, let's say, basic user of IDEA StatiCa Connection, I've got similar problem as before. The beam is bending towards the upper space, and so what can I do now is, of course, I would do a change of the forces into bolts. So now I should be safe, and now I should have my model correct. And let's see what's happening. Well, nothing really changed. This is strange. And also the deformation is not looking all right. Why is this so? Let's take a look at the wireframe model. Oh, the position of forces is still in node and didn't shift to bolts. This is because for some operations, as stub, for example, and other more complex operations, this option to force to move the forces to bolts is not working very well. This is working very well for fin plates, cleats, and other directly connected beam to column type of operations. So for this time, I have a third option to move the position manually. Okay, so I will input 300 millimeters because this is the length of my stub here. And let's take a look where the position of forces is now, and it's in the bolts. Good, so this is looking better. So let me prove that I'm on the good way. Okay, this is looking much better now. Let's take a look at the deformation. Yeah, this is looking good. I have the 80 times scale of this. All fine. Now, let's discuss just briefly what's going on here and why shouldn't I just stick to forces in node, because this is what I assume to have according to my structure model, right? For example, in SAP 2000 or other structural software where I have the whole construction. So let me draw a little bit. So let's take a look. Imagine the structure model. Just ignore my imperfect drawing. Imagine this is one column and a beam connected to another column, right? And I assume this is a hinged connection. So in SAP 2000, I would say there are hinges, and then the moment distribution would look like something like this, right? This is my moment. I can say it's minus moment, right? But take a look at the real model, as this is what we have in IDEA StatiCa Connection. The hinge in reality is not in the node, right? This is just a theoretical hinge that we use as a simplification for the structure model. In reality, the hinge is here in the bolts. So let me draw the real example. So again, a column and a beam. I hope this is visible for you. And the hinge is here, and here is just a rigid link, as well as probably something similar would be here, right, on the other side. So then, if I change the color for the moment, then we would have something like this. And here it would go up and up. So here I have moments of minus, and on the ends, I have a positive moment, right? And this is the reason why we have to shift the shear force in case we have a pinned model, when we have a hinge, to the position of the bolts where the real hinge is, right? I hope this is understandable. Now, just one last comment to this. I assume this stub connection is pinned because the plates are very thin, the bolts are in the center and are small as well. So in case I don't have a pinned connection, which I can, by the way, very easily confirm by running the stiffness analysis in IDEA StatiCa for any connection. So in case this is not a pinned connection, but let me edit this a little bit. Let's say I have a very thick end plates for the stub, and I have more bolts here, something like this. This is looking more rigid. Probably this would be something like a semi-rigid connection. Now, if I calculate this with the position in node, let's see what's going to happen. Well, this is looking okay on the first side. I've passed the code checks, everything looks okay. So why any suspicions? But very good tip from my side is to always take a look at the deformation trends and what's going on in the model. Here I can see again, this is not looking good, right? Again, the beam is rotating and bending upwards. Why so? Because take a look at the forces. I said this is now a semi-rigid or more rigid connection, right? I have only shear force. That doesn't make sense. If I have semi-rigid connection, I have to have a bending moment as well. So I'm just missing a moment in here, right? This is what I would read in my structure model in SAP 2000 if I set this structure in the structure model, this connection as semi-rigid or rigid. I would have shear force and moment. So now let's take a look how the results will look like. Something, let's say, similar on the first side. Code check passed. Something is happening here. I have some stresses in the welds in the column web and so on. And if I turn on the deformation, this is looking much better. And this is what I want to calculate and analyze. So that's it for the position of forces and the setting of forces. You can find it here and display the moment diagram in the wireframe view. Okay, so
Okay.
I can conclude
Thank you,
this.
Adam.
Jan, tell me. You're welcome. Tell me what next do you have there?
Yeah. Thank you for explaining the first one. I really like the second example. It was more advanced, but overall nicely explained. Now, if we should move on to the next very oftenly asked question by the structural engineers of IDEA StatiCa, which model type is the right one?
Okay. All right. So by chance, I can summon another simple model where I can nicely demonstrate this this topic or this pane. Let's say I have just a column, a beam connected by a cleat operation, and I use this cut to lengthen the column. So very simple model. I have a shear force only because this is a pinned connection, of course. And the model type is located next to the forces location, as I demonstrated previously. I have 4 model types: a full model type where I allow all 6 items of the internal forces. That means normal force, shear forces, and all 3 moments. And then I have 3 restricted model types. In this one, I restrict the sides. In this one, I restrict the verticals. And in this side, I restrict the moments. So let me show you what's going on with these model types. If I leave the default one, the general one, that's for the most cases, for the most scenarios, most used models. This is for 90% the correct one. So I have calculated this, and if I take a look at the formations, everything is looking good. I can scale this up as well. This is just the correct setup. Yeah, fine. But what happens if I start to play with this? So if I change the model type to restrictions in the horizontal line, that means I neglect all shear forces and bending moments in the horizontal level. So let me calculate this now. And let's show what's going on. Well, actually nothing special. This is exactly the same as the previous model type because I have just a shear force in vertical, so the model is not affected in any way. Also, the cleat is on both sides, so everything is symmetrical as well. So I have no rotation of the beam due to unsymmetrical connection or something like that. Right, so that was pretty easy, nothing special. Now what's going on if I restrict the vertical? No shear force in the vertical way, no bending moment. I can check this here. These values in here get grayed out. If I calculate the model, let me see the results. I have something extra in here, and if I turn on plastic strain, there's no deformation at all. Even if I scale it up to 100, that's the maximum. This is not really moving at all. This is all dead. Let me see stresses, all 0. There's no stress at all in the model, so nothing is going on. And it's because I restricted the shear and the vertical, and I can see that the software is informing me in this non-conformity tab. I can see I have restricted 100 kilonewtons in Z direction in the vertical, and I have restricted some rotation around y-axis. So that means bending moment my in global coordinate system. So where are these forces now? They were basically consumed by this restriction, and this works as a support. You can imagine this as a support in a structure model that you input on this free end in here. So let's see about the wireframe. I can read here, I have this 100 in vertical that was consumed by the support, and this 13.9 of the bending moment that was consumed as well. So of course, this is not correct. And then the last type, the NVV. Let me see. This is quite often used model type. I'll tell you why in a minute. This time I have calculated something. It's looking quite okay. Also the deformation looking like should be correct, right? This is just dropping down and bending downwards. Okay, I have some non-conformity, which is 0.4 of a bending moment. That's, let's say, almost nothing when I have 100 of a shear force, right? So it doesn't look bad. In fact, this is almost correct. But what is the difference? Let me show you that. I will create a screenshot of this image. I can close this one. Okay. And in the model, I will go back, switch to the default general type, and demonstrate the difference in the behavior. So let me summon the picture in here, zoom it a little bit. So I have both scales of 100 times the ratio. You can see the deformation is slightly different. The model where I restricted the moments is bending a little bit less, right? So what means this non-conformity in here? If I can draw this in here, so I would imagine this is the beam deformated as in the general type on the left side. So this difference in the deformation is caused by that this model type NVV consumed a little bit of the moment that produces this deformation. So now the question is, where should I use what? So the general one is recommended to use for any kind of connections. These side restrictions means the beam closely at the location close to the connection I'm analyzing here is somehow supported in this way. There are, for example, side beams holding this beam in position and taking the loads and stresses in this direction. Same in here. This is now supported by some column in this place. And the last one, this means that this beam doesn't take any moment loading. So this is typical for, let's say, diagonals and wind bracings and so on. All these beams that are loaded mainly by tension or pressure. So that means normal forces and some shear forces. Okay, so that's for the model type. You can find
Adam,
it here, and you now are familiar of the differences.
Thanks
So
for summing this up for us and for the
yeah,
viewers.
yeah. Jan, again, shoot me with the other one.
The other one is, I'm really interested in this one. If we have a nice model, the 3D scene looks nice and clean, but we still get a bold error. What should we do?
Mm-hmm. And you struggle with this and so on, right?
Right.
Unhappy user, let me help you with this then.
Please save me, Eren.
I'll be most happy to do it. So again, accidentally a modal in here that I can summon to demonstrate this thing. So what I have here, again, a column, a beam that consists two U and P sections. What I have here for loads, shear force and moment, since this is some kind of semi-rigid joint, right? I have just the basic stiffener, and I have 3 fin plate operations. For this, I have used the editor here to shape the plate a little bit so it looks nicer. The same in the bottom, that's the fin plate 2, and fin plate 3 is inside. You can see it in here. Here I inputted the bolt and deleted these bolts in here in the editor using this function to edit the bolt. Okay, so this is looking pretty well, right? I've got pretty decent model. Everything looks okay. So let me calculate this. Okay, I've got some error. So what's going on? The model would not calculate because it tells me that bolts are too close to plate edge or outside of the connected plate. That's pretty strange because I can see everything is in place. But let me study this operation a little bit of the fin plate. So what I have here is that I'm connecting member B, which is this one, and I'm connecting, I can turn on the plates information. I'm connecting its top flange number 1. If I zoom in, that's the right part of the composed U section, right? And I'm connecting to the member C, which is the column. And then I'm just setting up the dimensions of the fin plate, bolts, and welds, and so on. So what I'm missing here is I didn't connect the bottom flange to the other part of the composed section. So I've completely neglected this. I can't do this. So now these bolts on the left side of the fin plate are connecting just this plate and nothing in here. So that's why it's telling me they are outside of the connected plate, because they're trying to connect the top flange, which is missing in here. So what can I do with this? Let me show you a second example. I can redesign this, play a little bit more. That means spend, instead of 2 minutes of modeling such a connection, I would spend maybe 5 minutes of modeling this. So what I will do is I will model a general stiffening plate. That means this is this operation. I will model the upper and the lower one. I will add a bolt grid operation, which is this operation in here. And here I have more option of what I want to connect. So in this case, I'm connecting the stiffening plate and the top flange number 1 of the B member. That's correct. And separately, I will add another line of bolts for the bottom flange 2. And similar way, I connected the bottom of this. Then I add the stiffener. I cut the beam so it doesn't intersect with the column. And I add the fin plate to connect the web of the composed section and the column. Right, so now let me calculate this. I believe we are already suspicious a little bit that this is probably not the last word. And you are right, because what I want to show you here is if I go to check, everything looks okay. I've got the code checks, everything calculated, analyzed, I've passed. So all looks fine. But again, let's study what's going on. The formation looks okay, everything is good. Let's take a look to be sure on the stresses. So I've got some stresses here. This looks okay. I have concentration in the column panel. I've got some stresses from the bolts in here and on the other side. Whoops, this is not looking correct, right? I'm missing the bolts here completely. So I have to go back and investigate what's wrong. So if I go to the fin plate operation that connects my web, I can see again that this is connecting only web number 2 of the composed section, and I have also a web number 1 on the right side. So again, I have to redesign this a little bit. I'll turn off the fin plate and I will add a general plate inside the composed section and add the bolt grid. Oh, sorry. This is now, since I turn it off, I have to set it correctly. So let me show you that. I am connecting stiffening plate number 4, and I'm connecting web number 1 and web number 2 of the B member. Let me calculate this now. And see if I got any better. So again, go to check, just double check about the deformation, about the code checks. This is just a slightly different, but as I can see, when I turn on the stresses, I've got the bolt holes and all looks fine this time. So that's it. For the splices, this takes this phenomenon of using, let's say, some advanced operation as a fin plate to connect more than 2 plates. That means I'm connecting 3 here. Then it is necessary to use the general operations, the stiffening plates and bolt grids, to model this correctly. Cool, so that was the last word for this. Question of yours, Jan, and you've got one more, right?
We have one more, the last one, and the question is why we can't cut or use the splice operation on Stub.
Okay.
What do you think?
Again, I assume you have created a model, everything looks okay, but you have some error again. Disappointed. Let's take a look. So I'll demonstrate on this model this time. I've got a column. I've got one member shifted by 500 millimeters towards the free end. And I've got a member that should be connected to the column. So now, and some forces as well, of course, and now I want to create the stub. So what can I do? What I did first, or actually what you did first, what I'm showing to the others here, sharing the workflow, which didn't let you good end, but that's the best way how to learn. So I created a work plane in the place where I want to have the stub connection. I cut the right part of the beam by this. Then I cut the left part of the beam by the column. That means I welded this at the same time. And I create a splice operation. That is this one. This operation provides me plates on both sides and sets of bolts, and everything is just inputted in here. So this is looking okay, no problem at all. When I push the calculate button, it doesn't even tell me any error. So why should I bother? What's wrong? Let's take a look. Turn on plastic strain, mesh deformed, the favorite combination of checking the outputs. And I can see something wrong is happening here. What's that? Then run the equivalent stress. I can see there are some strange spots on the mesh. Let's see if I over ratio the scale of deformation. I can see there is something definitely wrong, right? I have two beams in here. One is somehow loaded and bent, and the other one is not loaded at all. This is because when I use the splice operation, in this case, it created another overlapping part of the member on the right side. So now I have two. And this is, of course, not correct. So this is not the good way how to do this. So let's see about another way. So this time I deleted the free end because it was doubled. And I left just one beam, okay? And I will use a stub operation instead of that. Stub operation is this one, or this one, or this one. So in this case, okay, the stub was created. It's this part. My beam is here. And I want to have a, let's say, a hole in here. I don't want to have this plate. I don't want to have welded stub. I want my splice, right? So what I'm going to do, I will basically say this plate has 0 dimensions and I turn off the welds. So this is how I got rid of this, and I have just this nice 5 millimeters thick hole between the stub and the member. And then again, this is what I already know how to do. Add my splice operation, connect these two, and cut this part of the stub by the column to weld it. Okay, this is looking very good now. Let's calculate. And whoops, there's the error. Plate area is too small. Stub end plate. Okay, what a mess. Let's see. Stub 1 is this one, and end plate is probably the plate that is generated by this operation, which I set as 0. And this is what the software doesn't like. It doesn't like such workarounds. So this means this is not a good way. It would not allow me to calculate a model where I have a plate with 0 dimensions, because the plate is still as a part of the model, just it has 0 dimensions and I can't see it in the 3D scene, but from the point of view of the data of the model, it's still there, and it's making mess. So there's a third option, and I promise this is going to work now. Again, I start just with the column and the beam, and I want to create a stub and spliced connection. So I start with the work plane, can cut the member by it, as I did at the first try. Then I can create a stiffening member, which is another operation that I can find here. For the stiffening member, I just set the length here and the cross section, and it's placed in here. So that would act as the stub, right? So now I need to somehow cut this stub. So by this work plane, I will take advantage of that, what I already have, and the other end, just cut and weld. And the last thing, this is now looking okay. I have even a small hole in here. This is because for the cut of the stub by the work plane, I inputted -5 millimeters to produce this 5 millimeters hole. And last, I will input the splice. Say I'm connecting member 2 by 1, and I'm connecting the SM1, right? And again, the same parameters as before. And now, finally, let's take a look. Okay. This is calculated. The deformation trend is looking okay. Stresses, everything is just fine. So this is the good way how to model such a splice on a stopped connection. So Jan, I hope you feel more relaxed now, more happy, more happy how to correctly model these things and avoid all these mistakes and sideways. Okay, so I think that was the last word. Good. That was the last word from my side. And you have something more to say to conclude this session, right?
Yep. Thanks, Adam. Thanks for explaining the last question, and not just the last, but all of them today. Thanks to Adam. We know what should we do in case we want to have the correct position of forces. If we want to know which model type should be used. What should we do if we get a bold error on the perfectly looking 3D scene? And also, what should we do if we can't cut or use the splice operation on the stub? Okay, so thank you for that, Adam.
Right.
Obviously, it might happen that our users have a different kind of issue or questions. So what should you do? It would be nice to get Adam on the phone in all of those cases and discuss with him. But it's certainly not the fastest way. So if you want to solve your issue quickly, go to IDEA StatiCa webpage, click on a support center, type in the keywords of the issue that you're dealing with, and scroll through the results. You can, of course, filter through them based on an application, on material, on different type of content or the code. So this is definitely the fastest way. And if you mean it seriously, if you want to really take your connection design on the next level, we can help you with that. On IDEA StatiCa webpage, there is a campus subpage, so join the IDEA StatiCa campus, or down below on IDEA StatiCa webpage, there's an e-learning category, so just click it. Register for the campus. The first lesson, introductory lesson, is for free. And then you can assign the course. It takes 20 to 40 hours based on your knowledge level. And after that, not only that you will have a lot of advanced information about connection design, but also you will get your own flashy certification, and you will become IDEA StatiCa Certified Connection Design Professional. Okay, so
Cool.
I think we covered a lot today. Thank you very much for being with us, and please do take care. Bye-bye.
Thank you. Have a nice rest of the day and enjoy. Bye-bye.